Good afternoon, and thanks for inviting me to give this talk. I am Jayan Thomas, and I am a professor of Nanoscience Technology Center, as well as College of Engineering and Computer Science and College of Optics and Photonics. So I'm going to talk about how to fine-tune the materials band structure to make new energy storage devices, as well as neuromorphic optoelectronic devices. So this is my research group in at nanoscience and UCF. I have two directions in my research. One is the energy direction, and the other one is the optics and photonics direction. So energy direction, we work on supercapacitors. That's an energy storage device, wearable devices, perovskite solar cells, integrated energy storage devices. And from the optics point of view, we have other directions like superstructures and optoelectronic synapses, nonlinear optical materials, and organic electrochemical transistors. So today I'm going to talk about supercapacitors, energy storage devices, which can be used as the structural components of electric vehicles. And also I will touch on the superstructures and optoelectronic synapses, which can be used for neuromorphic computing. So the motivation behind this work, as at least some of you guys already know, your laptop, it can stay on charge maybe for about 7 to 9 hours for a single charge. But if you have an electric vehicle, for example, to get a mileage, that is the acceleration from 0 to 60 miles in less than 2 seconds, you need a huge power. So there are two terms here. One is the energy density, and the other one is the power density. So the lithium-ion battery, it can give a high energy density, whereas the supercapacitors, it can give a huge power density. So this power density can be used to get that acceleration, but it cannot stay for a very long time. Whereas the battery, it stays for a very long time. So what we are trying to, if we can bring the energy storage capability of supercapacitors more towards the battery, so it can provide high energy density, at least a reasonable energy density, and a high power density. So how we can do it, that's what you can see here. Basically, currently all the aqueous supercapacitors, or the supercapacitors or storage device which uses the water-based electrolyte. Two things happen. At the positive electrode, there is a oxygen evolution, and at the negative electrode, there is hydrogen evolution if you exceed the voltage beyond 1.23 volts. So that is the window you use. So, but that is basically because once you come to this positive electrode, this is the work function of the material, and once you exceed this one, oxygen evolution take place, and once you exceed this Fermi energy level of the negative electrode, hydrogen evolution take place. So if you can engineer your work function in such a way that you can get a wide window here, then you can end up getting a high voltage supercapacitor. Why it is so important? Because energy density is given by this equation, half C into V square, where C is the capacitance and V is the voltage coming from here, and capacitance is directly proportional to the surface area. Here you can see a comparison of the different devices, but I am not going to into details. But the major difference is, for the lithium-ion battery, you have a bulk electrode where the ions diffuse, lithium ions diffuse into that one, and it takes time for that diffusion to take place when you have a bulk electrode. And that's the reason why it takes time to charge, and also it takes time to discharge those ions. Whereas in the supercapacitors, you can enhance the surface area. The energy storage takes place at the surface or very close to the surface, but this can give out that ions or de-intercalate the ions very quickly. So that's the reason why it can give the huge power. So when you compare the performance of these two devices, batteries and supercapacitors, batteries high energy density, as I already told, but low power density, long discharge time, but inferior number of cycles. For example, 3000 to 5000 cycles for your battery, whereas in the supercapacitors, the energy density is low. Discharge time is also low, but high power density and high durability. It can go to hundreds of thousands of cycles. That's one of the important aspects. So why these energy storage are so important? You know, we all know that it's moving to electric vehicles by 2035 or so. It's many of the vehicles are going to be electric, and there are a number of issues for these electric vehicles. You know, where the energy can be stored, more energy can be stored. Now it is limited to whatever the 350 miles per charge, something like that. You know, it needs to go beyond that one. If you want to go beyond that, you can of course add more batteries. If you add more batteries, the problem is that it is going to add weight to your vehicle, and again it needs more power for that movement. What we think is a better idea to store energy in the structural components of these electric vehicles. So current problems with these electric vehicles are low miles per charge, high charging time, high battery weight, high upfront cost, and low battery cycles. And also, you cannot use lithium-ion battery as the structural component, basically because if there is an accident here, as you can see, this was a accident happened on Tesla, and it catches fire. It's flammable. At the same time, these batteries can fly, and it can land wherever, and it can catch the fire and all those things. But if you make these structural components of the electric vehicles with aqueous based electrolyte, the fire is basically because of the organic electrolyte, but we are going with the aqueous, the water based electrolyte, so that it can be safe. That's the direction we pursue. But what we have done in this case is we take this type of carbon fiber cloth, and if this is a carbon fiber, then what we do is we attach this type of graphene. As you know, graphene is a two-dimensional material. It has a huge surface area, and remember, your equation capacitance is directly proportional to the surface area. And here you can see the vertically aligned graphene on this carbon fiber. So what you're getting is a hugely enhanced surface area for the energy storage. So to add to that one, what we have done is we add certain other materials. These are called pseudo-capacitive materials, or one which can undergo the Faraday reaction to enhance the energy storage capacity of your device. So we add some transition metal oxides onto that one. We can just deposit it from the solution phase, and finally we make carbon fiber based composites. So carbon fiber reinforced plastic, that is the CFRP. But if you look at here, why it is so important, you can see that this graphene on these carbon fibers, it can go to whatever number of cycles. You know, this is a number of cycles. Okay, you can see the number of cycles there. It gives you a very stable performance for quite a long time, for 100,000 cycles. And when you add this type of pseudo-capacitive materials, what you can get is a highly enhanced storage capacity. You know, this is a cyclic voltammetry where the current versus voltage, and the area gives you the energy storage ability for your device. You can see once you deposit other transition metal oxide onto this surface of this graphene, you can highly enhance the storage capacity. And then we made that into a composite, and here you can see the performance, mechanical properties of that composite compared to a commercially available CFRP, which is given here. And you know, by making it into an energy storage device, still the mechanical properties are intact. That means the tensile strength is more than 80% of the commercially available sample, the carbon composite, and the impact energy is also similar to that of the carbon composite. And this can give a high energy density as well as high power density. And the intention is to make the shell of that car with this type of composites, as you can see in the next picture here. But in the next slide, you are going to see a video which shows that this composite is a very small area composite, and we use it for the application, real application. But what are the advantages of our composite? Just briefly, it is the electrical charge storage, high mechanical strength, the super lightweight, non-flammable, and super fast charging, high cycle life, low fabrication cost, and easy processing. But if you ask me, are there any cars or that runs on this type of supercapacitors? Yes, Lamborghini released this model with a booster engine that works just on supercapacitors, so that it can get that huge acceleration in the beginning itself. So that runs just the booster engine runs just on the supercapacitor. So going beyond that, what we have done in our lab itself, we can attach this type of solar cells onto these composites. And if you make the roof of the electric vehicles with this one, if the vehicle is in sun, it can harvest energy and store in itself. So to demonstrate these things, this composite can store energy, what we have shown is here is that this is the car, and we put that sheet of composite here and just to power this car. And this is a very short video, so that I don't take much time on this one, but you can still see, it is that piece of the carbon composite was pre-charged, and then that is connected to the motor of this car, and you can see that the car can run using the energy stored in that small piece. So you can see that the car can run just with that energy stored in that small composite. So the near-term goals, there can be a number of applications. For the NASA CubeSat, we are working with the Kennedy Space Center for that one, and UAVs, and for the DoD applications, as well as if you can use this composite to make the outer structure of the tanks, then that can store energy too. Even now, the Boeing Dreamliner, about 50% is made up of composites, mostly carbon composite. And if we can use those composites to store energy too, that would be really nice to move on to the electric aeroplanes and such things. So shifting my gear to the next one, again, this is that optics and photonics direction. What we have done is we are making some of the neuromorphic type platforms, synapses. So it is so important basically because this type of synapses, it can process and store information at the same time, which can save time as well as energy. So what we have done, we can start from the materials, synthesize materials, then process it, then make it into device, and then we can characterize them. That's the advantage we have in our lab. So we followed a method. Here is the graphene, and we grow this type of quantum dots from the lattice of this graphene and convert it to a phototransistor type structure. The advantage is that the total thickness of that active layer is maybe less than 20 nanometer or so, extremely thin. And they are, by graphene by itself, its light absorption capability is very low. It absorbs about 2.3% of the visible light. But by adding this type of quantum dots, its light absorption capability can be enhanced many times. So as you know, these quantum dots, especially the perovskite quantum dots we use in this case, it can absorb a lot of light and convert them into charges. So that's what we have done in this case. And by tuning the energy levels here, you can make these things, there can be photo gating effect, and you can give the memory effect to this film. That's the advantage by tuning the energy levels of the materials you attach onto that graphene. So it can, you can have tuned memory, you can get short-term memory as well as long-term memory. Like our brain, we have short-term memory and long-term memory. And long-term memory, typically if you see something for a number of times, you can get that memory effect for a long time. And here you can see a plot which shows that short-term memory, these are the short-term memory, and here you can see the long-term memory. So to demonstrate that, this is a gate driven property, and all those things that is given in that one. But to demonstrate these are good for that neuromorphic computing and that type of process, we have shown face recognition using these devices with the help of machine learning. But going beyond that graphene, we have expanded that work to carbon nanotubes. So we can follow a similar approach. You can have this type of quantum dots grow on these carbon nanotubes. And here we developed a two-terminal device and with a number of carbon nanotubes. But why we are doing it is basically you can go to a single carbon nanotube based devices that may be possible in the future. So here you can see some of the quantum dots grown on carbon nanotubes, the TM image, and even some of these quantum dots can grow inside the carbon nanotubes. Here, this is the pattern recognition using this type of devices, and here you can see all the properties, that is the pulse pair facilitation, current from the second pulse to the first pulse, and all these plots, it shows basically it can work like a neuromorphic synapses. And here in this case we use optical potentiation. Okay, for the potentiation we use optical signal, and for the depression we use electrical signal. So the going beyond that one, what we are aiming at is you can see that near-term and long-term goals, we can make all optical devices, which is going to be more fast and also energy efficient. And we can go to synaptic devices with the short-term and long-term memory, and we can tune the energy levels, and we can go to that level. And all these things we do by tuning these energy levels of the materials and to get that memory, short-term and long-term memory. And we use our rich memory on holographic photorefractive holographic display devices to develop this type of devices. And here, this is one of the images where you can see this carbon nanotube, multi-volt carbon nanotube aligned between the two terminals. This can be done electrically align these carbon nanotubes, and you can make devices. And finally, I would like to acknowledge all of our current graduate students, postdocs, and undergraduate students who are working in this area, and also the collaborators, especially Dr. Luke Robertson from Kennedy Space Center and Dr. Mohammed Hussain from Nissan Technical Center, North America, where we get a lot of information or whatever necessary parameters we need for this type of composites. And also from UCF, Dr. Tanya Roy and Dr. Caitlin Crawford for some of this neuromorphic work, and of course all the financial support from NASA, NSF, and some partially by Department of Navy, and some is coming from Nissan too. And thanks for your attention.